I am Lathashree from first year MSc. You are watching a video on a theorem of uniform convergence and continuity. Let us state the theorem. Suppose K is compact and first condition sequence Fn is a sequence of continuous function on compact set K, and second one, sequence Fn converges pointwise to a continuous function f on K, and third one is Fn of x greater than or equal to Fn plus 1 of x for any x belongs to K. That is, sequence Fn is the decreasing sequence for any x belongs to K, n equal to 1 to 3 and so on. Then we have to prove that Fn converges to F uniformly on K. Let us see the proof. These are the given conditions. By third condition we get Fn, each Fn is the real valued on K for any n. Let us define a function Gn such that Gn satisfy all these conditions. Define Gn as Gn is equal to Fn minus F for any n equal to 1 to 3 and so on K. Since Fn is a continuous on K for any n equal to 1 to 3 and so on, and F is also continuous on K, that implies Jn is equal to Fn minus F is also a continuous function on K. And given that Fn converges to F pointwise on K, that implies Gn that is equal to Fn minus F, which is converges to 0 pointwise on K. And also Gn of x is equal to Fn of x minus F of x. We have Fn of x greater than or equal to Fn plus 1 of x. Since Fn is a decreasing sequence, therefore this is greater than or equal to Fn plus 1 of x minus F of x, which is equal to Gn plus 1 of x for any x belongs to K, n equal to 1 to 3 and so on. This implies Gn of x greater than or equal to Gn plus 1 of x. That is nothing but sequence Gn is a decreasing sequence of real valued function converging to 0 pointwise. Therefore, Gn of x greater than or equal to 0 for any x belongs to K and n equal to 1 to 3 and so on. Therefore, we defined a function Gn such that Gn is the continuous function on K and Gn converges to 0 pointwise on K, and sequence Gn is the decreasing sequence of real valued functions converging to 0 pointwise. Now we have to prove that Fn converges to F uniformly on K. So let us claim that Fn converges to F uniformly on K. To prove this, it is enough to prove Gn converges to 0 on K. This is nothing but to prove this, for any epsilon greater than 0, there exists n belongs to n such that modulus Gn of x minus 0 less than epsilon for any n greater than or equal to n. To prove Gn converges to 0 uniformly on K, we have to prove these conditions. So let epsilon greater than 0. Now we have to find such integer n belongs to natural numbers such that these conditions will hold. So that let us define, for each n belongs to z plus, define kn is equal to x belongs to K such that Gn of x greater than or equal to epsilon. This is equal to Gn inverse of the set epsilon to plus infinity. Here Gn of x greater than or equal to epsilon, therefore x belongs to the set epsilon to plus infinity. Since the set epsilon to plus infinity is closed in R and Gn is continuous function on K, we note that Kn is closed subset of K for every n. Since this set is closed in R and Gn is continuous on K, Kn is closed subset of K. We have one result, that is closed subset of compact set is compact. Therefore, here Kn is also a closed subset of the compact set K, hence it is compact. Further, Kn is greater than or equal to Kn plus 1 for every n. In fact, to prove this, any element belongs to this kn plus 1 also we have to show that element also belongs to kn. If x belongs to kn plus 1, by the definition of kn we have gn plus 1 of x greater than or equal to epsilon, but gn of x is greater than or equal to gn plus 1 of x. Since gn is a decreasing sequence, therefore gn of x greater than or equal to gn plus 1 of x. That implies gn of x greater than or equal to this epsilon. This implies x belongs to kn. Therefore any element x belongs to kn plus 1 also belongs to kn. Therefore kn is greater than or equal to kn plus 1. And another condition, intersection of kn n from 1 to infinity is empty. Suppose not, let x belongs to uh, intersection of kn n from 1 to infinity. That implies x belongs to kn for every n equal to 1, 2 and so on. This implies gn of x greater than or equal to epsilon for every n equal to 1, 2 and so on. This implies modulus gn of x minus 0 greater than or equal to epsilon for every n equal to 1, 2 and so on, which is a contradiction to the fact that gn converges to 0 on k. Gn converges to 0 on k, that implies modulus gn of x minus 0 less than epsilon, but here we get modulus gn of x minus 0 greater than or equal to 0. Therefore it is a contradiction to the fact that gn converges to 0 on k. Therefore this intersection of kn n from 1 to infinity is empty. Thus the sequence kn n equal to 1, 2 so on is a decreasing sequence of compact subsets of k such that intersection of kn is empty. Therefore there exists an integer n belongs to z plus such that kn is empty. That implies that gn of x less than epsilon for any x belongs to k. Therefore, since we define kn is equal to set x belongs to k such that gn of x greater than or equal to epsilon, but kn is empty, that implies for any x belongs to k, this is gn of x not equal to epsilon, therefore it must be less than epsilon. And we have sequence gn is the decreasing sequence. Therefore for any n greater than or equal to n, gn of x must be less than or equal to gn capital N of x. That implies gn of x less than or equal to capital Gn of x, g capital N of x, that is less than epsilon. That is gn of x less than epsilon for any x belongs to k and for any n greater than or equal to n. That implies modulus gn of x minus 0 less than epsilon for any n greater than or equal to n and for any x belongs to k. Thus we proved that gn converges to 0 for any epsilon greater than 0. We get an integer n belongs to n such that modulus gn of x minus 0 less than epsilon for any n greater than or equal to n and for any x belongs to k. Therefore gn converges to 0 on k. Hence the claim. Hence the theorem. Let us see the note. The condition k is compact cannot be dropped in the above theorem. That is, k is compact is important in this theorem. For example, consider the function fn of x equal to 1 by nx plus 1. X belongs to open interval 0 to 1 and n equal to 1 to 3 and so on. Note that the sequence fn is a sequence of real value continuous function defined on open interval 0 to 1, which converges to 0 pointwise on 0 to 1. That function sequence fn converges to 0 pointwise on 0 to 1. Further, it satisfies fn plus 1 of x less than or equal to fn of x for any x belongs to open interval 0 to 1 and for any n equal to 1 to 3 and so on. How this happens means, since n less than or equal to n plus 1, that implies nx less than or equal to n plus 1 of x, which implies nx plus 1 is less than or equal to n plus 1 of x plus 1. That implies 1 by n plus 1 of x plus 1, which is less than or equal to 1 by nx plus 1. Thus fn plus 1 of x less than or equal to fn of x. Thus, sequence Fn satisfy conditions A, B, C of the above theorem. But still, convergence is not uniform. Suppose Fn converges uniformly to F on open interval 0 to 1. Then for any epsilon, take epsilon equal to 1 by 3, which is greater than 0, there exists n belongs to n such that modulus Fn of x minus f of x less than 1 by 3 for any n greater than or equal to n, and for any x belongs to open interval 0 to 1, which is nothing but 1 by nx plus 1 minus 0 less than 1 by 3 for any n greater than or equal to n, and for any x belongs to 0 to 1, which implies 1 by nx plus 1 less than 1 by 3 for any n greater than or equal to n for any x belongs to 0 to 1. In particular, for n, 1 by capital Nx plus 1 less than 1 by 3 for any x belongs to 0 to 1. Let x equal to 1 by n, then 1 by n into 1 by n plus 1, which is less than 1 by 3. Here n cancel, 1 plus 1 2. 1 by 2 less than 1 by 3, which is a contradiction because 1 by 2 greater than 1 by 3. Here we get 1 by 2 less than 1 by 3, which is a contradiction. Therefore, Fn not uniformly converges to F on open interval 0 to 1. Note that here domain 0 to 1 is not a compact. Therefore, even though this sequence Fn satisfies all the three conditions of the above theorem, but still convergence is not uniform.